Hello, everyone, and welcome to our webinar today, Quantum Programming 101, Solving a Problem from End to End. So we're very glad you could join us today. Some of the webinars that we do are really intended for people who are familiar with quantum computing and quantum programming and familiar with D-Wave, and we really wanted to target this to people who are new to the subject. We'll also be interested at the end to find out what other kinds of topics you think would be useful to you. We do these webinars monthly. We do record them all, and they wind up on our YouTube channel in the webinar playlist a day or two after we are done. So a few housekeeping notes before we get started. First of all, you will note in your Zoom box there is both a chat and a Q&A. So during the course of the talk, we have a number of expert panelists standing by. And if you have questions about the contents of the presentation or questions overall about quantum computing, you can put them into the Q&A box. Please don't use the chat box for questions, but we're happy to get chat messages from you, or if there's anything outside of the subject matter that you would like to let us know about. But most of the questions will be answered during the talk, but we will mark some of them to have our speaker answer at the end. So with that, I'm going to start recording, and then I'm going to introduce our speaker. Okay, great. So let me introduce Joel Gottlieb. Joel joined D-Wave in January 2016 as a senior pre-sales analyst after spending 20 years in AT&T and AT&T research. He earned a PhD from the University of Wisconsin at Madison in condensed matter physics after graduating from the University of Michigan. At D-Wave, Joel's role includes bringing new uses to the quantum computer and researching basic problems which show the power of the system. He loves learning new subjects and new technology and also enjoys talking music. So with that, I'd like to turn it over to Joel to get us started.
And thanks very much, Susan. Welcome to Starting from Scratch, Solving a Problem from End to End. And what we want to do today is different than a lot of the videos that you can see, but it'll fit right in with them as we go. You'll see why. And first, a big shout out to my colleague Victoria Golieber, who is in Korea at the moment and wrote this talk, but isn't available to give it because it's the middle of the night there. And maybe some of you are in that situation as well. But thanks for listening and welcome. So what we want to do here is work through a complete problem. A lot of the trouble that people have to get started on the D-Wave system is that they don't know how to take a problem that they have and convert it to something that can run on the machine. And I think this is true for the field in general, because it's also true in the gate model architectures. You really have to know how to break a problem down and translate it into something that the computer can deal with. And someday in the future, there will be tools that do all of this for us, but those don't exist yet. And so I think it's a great benefit to go through a complete problem. As we'll see, this problem is a simple one, but if you think about it really carefully, almost anything you've got out there probably reduces to this, or at least a little bit of it reduces to this in one way or other. And I'm hoping to convince you of that by the end, and also hoping that you'll get interested and sign up for LEAP and contact us and maybe let us help you solve your problem and use our machines. So what we're going to do is go over what is our problem, how do we formulate it, how do we write a program to do that, and then how do we tune it. So first, what is the problem that we're going to look at? Let's take a group of people that we have, and we want to divide them into two teams and equal teams. And people want to be on a team with their friends. And so I hate to bring it up, but this reminds me of childhood when it was gym class and you had to sit there and be divided. And luckily, we're not solving it in that way because there's not people who are better than others in whatever sport it is. In this case, it's just there's going to be reds and there's going to be blues, and we need to divide them up into two teams. And also, we want to keep people on the team with their friends, much as how it was chosen in childhood. And the edges, in this case, the relationships are given. And they're drawn here. In this case, you can see that there are 8 people drawn, and there are relationships. And so what we want to do is set up the reds and the blues to follow a certain principle, which is that we don't want the red and blue to have edges connecting them. In other words, we want as few red-blue connections as possible. So how do we do that? And taking a 30,000-foot view of it, you start guessing red and blue here. And let's go through, instead, the logical process of mapping this problem and running it on the quantum computer. And again, as I said before, this is small, yes, starting out with a couple edges, etc., blah, blah, blah. But we have been releasing things, if you catch up on what we've been doing, that can handle much bigger and bigger problems. And so underneath a much bigger problem is also principles like this. And that's why I'm hoping we can get you interested in this, and also that you follow me. And if you don't, as Susan mentioned, please ask the panel. I'm going to try to work this through in careful detail. So here are the reds and the blues. And what we want to do is find a solution such that there are no lines, or at least as few as possible, connections between different colors. So if you can see the ones there, like across the middle, we don't want that one, the one that's horizontal there between a blue and a red. But somehow we've got to allocate the reds and the blues in order to do that. So how do we formulate this problem? And we need to formulate this problem as what is called binary quadratic model, or BQM, is D-Wave's name for a unification of 2 different models that hopefully some of you have seen before, and if not, that's okay too. One is called QUBO, which stands for Quadratic Unconstrained Binary Optimization. And that is a quadratic equation in binary variables with zeros and ones. In other words, we might assign blue to 1 and red to 0. We'll do that in a moment. But we will do something with binary variables in QUBO, or we also could do it with binary variables in what is called the Ising model, after the physicist Ernst Ising, who worked out a one-dimensional problem in the 1920s in Europe. In that case, the variables are -1 and 1. And you can formulate them either way. And something that in software sits underneath them, but conceptually but conceptually represents both, is BQM, binary quadratic model. So what we want to do is code up the problem and let the quantum computer or solver, whatever we use, find the values, the zeros and ones or the -1s and +1s that will solve the problem. Okay, so this is what we always need to do to run a problem on the D-Wave quantum computer. So first, we're going to do, in this case, we're going to pick QUBO. And we'll talk about why we do that. Mathematically, it's a little easier if you're a beginner. Some of you out there, if you're a physicist, you've seen Ising models, or maybe you've seen Ising models, and you're familiar with the -1 and 1, but bear with me, they transform into each other. So whichever way we do it because there's advantages to doing it this way. The process of developing Ising or QUBO or BQM is as follows. You write out your objective and your constraints in your problem domain, whatever it is. You convert your objective and constraints to math statements with binary variables. You make them QUBO appropriate. We'll talk about that coming up, where there's an objective, something to minimize, and constraints that you want to satisfy at minimum values and combine, and then get it ready for the computer by writing a program. So a BQM equation, or QUBO has two parts. What are we trying to minimize, the objective? And an example of an objective that I'm not covering today is traveling salesman problem, where the UPS driver or Amazon driver wants to cover as many houses as possible on her list in a given day and cover as little distance as possible during that day so she doesn't double back. And the distance might be the thing we're trying to minimize. It might be the objective. But in this case, it's going to be minimize the number of friends that are split up. In other words, if they're on the same team, they don't have edges connecting them. But if they're on a separate team, they've got an edge connecting them, and we want to reduce down to as few, of those connecting edges as we can. And the other constraint, well, actually the constraint that we want to satisfy is the team should be the same size. And again, back to that crummy childhood experience for a lot of us, unless you were one of the great athletes, the two teams were supposed to be the same size, and I always got picked last back in the day, which some of us, that may have happened to. So let's call the teams Team 0 and Team 1 for red and blue. And in this case, we'll color the red ones for each individual that we have, in this case marked by X. X of 0 is person 1. That'll be 1 if it's red, and blue if it's 0. And you get the idea here. There's X1 and so on until X7. So we're counting starting from 0, as a lot of programmers like to do. Hopefully you get the idea. That in that way, we'll mark which one's on one team and which one's on the other. So what's the objective? We'll get to that first, and then we'll do the constraint. The objective in words is minimize the friends that are split up. That is, minimize the edges with different color endpoints. And as I mentioned at the outset, the edges are part of the problem that was given to us when we started. It was a graph, and it had nodes, that's the people, and edges, that's the lines. And so we want to minimize the edges with different color endpoints, or that is the people who are split. And so as some examples here, this one, if I assign the blues opposite each other like Victoria has shown, across that one that's across the diagonal, that's good, right? Because they're both blue. And then the next one there, they're both red, that's good. But if something like this happens, where one is red and one is blue, I don't want that. Or at least I want as few of those as I can get. And so the question is, how are we going to do that? How do I tell the quantum computer to find me solutions that have that in it? And so just a quick analogy to this is, if you're out there and you've got problems with satellites that are allowed to be in certain orbits at a certain time, this might correspond to having two in the same orbit that are not allowed, things like that. Or you're trying to put together a stock portfolio, and you're only allowed to buy so many. And that's what I mean by real-world problems sit on top of this kind of thinking. So if I can get you to understand this, then we've gone a lot of the way down what you have to do to make a problem work. All right, how do I write this out mathematically? There's only 4 possibilities with 2 binary variables. Binary variable I representing person I and person J as the other, and you can see blue and red and blue, and red are the 4. And what we've written in there on the right is I have the states blue and blue are good, I want that, and I don't want the middle two, you know, the second and third lines, in other words, with the blue and red or red and blue. Those are both okay. And I want to penalize those somehow. And the red and red is also good. So hopefully you've got the idea, and now what we have to do is make this mathematical. And the first step is to put in the cubo variables, zeros and ones. Zero in this case corresponding to blue and red corresponding to one, and doesn't have to be that way. That's just the step that we chose. You could do it the other way around, both work. And then one more step now, and this is the key here, is to assign values to either one. And in this case we make, just by default, the 0, 0 and the 1, 1 solutions, make those value of 0 and make the other two have the value of 1. And why did I pick 1? I could pick a half, I could pick 74, I could pick whatever, but in this case, this will work just fine. We're going to solve this problem, and I know some of you people out there that are familiar with all this are saying, oh, but the gap. What about the gap between the energy states? Yes, yes, indeed. In this case, 1 is good enough in this problem, and that's a whole messy, complicated topic of gap size and so forth, but we'll pass on that for now because we're just getting started in this problem. The point, though, is that we put this in a mathematical form. So now, how do we do this? And the equation that is where it says we need our values to fit the form, where did that come from? If you look at it, it's the most general cubo that you can write for an xi and an xj. How do I know that? Well, look at the first term, AIXI. AI is some number called a bias, and it's just a linear term. The second term is some AJ times XJ, and then we have one coupler between them. That's the quadratic term. And remember I said it was called quadratic unconstrained binary optimization. You're not allowed to have xi divide by xj or anything like that. We only allowed these terms, and then we have an overall constant as well, which we will talk about toward the end. But the main point is there's no other possibilities. Now, some of you are thinking, hey, wait a minute, what about xi squared? That's a quadratic term. And you're right, except that if you think about it for a second, xi squared is the same as xi as long as you're using 0 and 1 variables. In other words, 0 squared is 0, 1 squared is 1. So I can get away with this. And in Ising, it is different. Because in that case, it's minus 1 and 1, and they both square to 1. And this would look a little different, but we just do the algebra there. But anyway, onward. I put in xi and xj like I've got there on the left, and you'll notice there on the right side, substituting in and notice that in the case of the top row there with the zeros, there's nothing there. The AI gets multiplied by 0, the AJ gets multiplied by 0, the BIJ gets multiplied by 0, and if I want that value to be 0, I have to set C equal to 0. And there's a little more algebra after that. I'm assuming that algebra doesn't scare you or that you remember it. And what happens, as I just said, C equals 0. And if I continue, then I get the next one. It says 1 has to be a sub j plus c, but c is 0, so a sub j is 1. I do the next one, there it is. And I do the one after that. That's going to lead to 1 equals a sub I. And finally, we do this last one. Little more algebra. AI plus AJ plus BIJ plus C has to be equal to 0. And when we do that, B sub IJ is minus 2. And we've got it. This is the solution that is going to tell the quantum computer to favor the solutions that are 0 and 0 or 1 and 1, and to penalize the solutions that are 0, 1 and 1, 0. And just a quick shout out to some folks at Los Alamos National Laboratory that have been studying behavior of large communities and online communities and things like that, and terror networks. All of that is based on this, taking pairs of people and seeing whether they've got a relationship or they don't. So this little fundamental problem turns out to be really important. So now, I'm not interested though in just picking 2 of them. I got to do it for all of them. And so the way to do that is just to take the step there for it's a minimum. I want those pairs, I want those solutions, xi plus xj minus 2xi xj. That's our solution from the earlier slide. I want to do it for all edges. And if I can minimize some of them, then what I'm doing is reducing the number of red-blue connections that I have in the graph. And I hope that's clear. If I sum up over all the edges that I've been given, I'll get the smallest number I can if I can come up with a solution to this. Okay? And notice things like setting all of them to 0, that doesn't work because the teams are supposed to be equal. And so let's get to that. That's the constraint. And that's the next thing. So just an aside, as I mentioned, we're only looking at the pairs with a relationship. So now, on to the constraint. The teams are supposed to be the same size. What does that mean? It means that half the variables have a value of 1. So the equation I need to write is the sum of I equals 0 to 7 of x sub I is equal to 4. And this is fairly clear that if you wanted to generalize this, just for those of you thinking about it there, how about 100 people? Okay, sum from 0 to 99 should be 50, right? I want to divide it in half. Now, what we need though is a constraint that's satisfied at the smallest value. And so this involves something interesting. If you think about it, there's 2 ways to go here, right? The sum of those xi's could be bigger than 4, but it could also be lesser than 4. And so on the right there, you see a straight line drawn, and a linear relationship is not going to do the job here, right? Because that's going to go into the negative on the left side, and I'm going to keep going down. So I need something that starts up higher, goes down, and comes back up. And what does that? That's the simplest form is called a parabola. And again, shades of high school, for those of us that loved math, you remember it, but if you hated it, please don't be too afraid. There's parabolas everywhere, and it will come back to you if you get a little time to look at it, that a parabola has 1 minimum there at 4. And so what we have to do at the bottom on the left side is sum up the x sub i's and subtract off 4, and then square it. And that will bottom out in one place and give me the solution that I want. And so now we're going to put them together, and we're going to end up with the stuff that I did before, that 1, 1 minus 2 solution over all edges on the left, and on the right is a constraint. And then there's a funny thing there with the number gamma. It's a Greek letter, and that is called a Lagrangian parameter. And I like to think of it as a fudge factor. The thing on the left might have units. In other words, it might be miles, it might be distance, it might be money. The thing on the right isn't. The thing on the right is just a constraint that has to be 0. So we have to put some number in there, and we'll come back to this. As we go forward here, we're going to use it with a value of 1. But we will see later that that had an impact on what we do. All right, how do we write a program? To write a Python program, we need to put the linear and quadratic coefficients from this quadratic unconstrained binary optimization, QUBO, into a matrix. And the Ocean Toolkit, which D-Wave offers freely downloadable, which I'm actually personally very proud of, having watched it grow and take shape and become really solid over the last couple of years, doesn't require the lower triangular part of it. It just requires the upper triangular. So, how do we do this? What we've got here needs some help. If you look at the thing on the right with the 4, that's algebra. That doesn't look like that QUBO form I showed a little while ago. So we got to do some algebra. And at the bottom there, the 3 terms that come out, multiplying that out. Actually, there's 4. Let's go through them. First, you see a sum over xi squared. Sum from 0 equals, from 0 to 7. And that, as we talked about earlier, that's just going to reduce to x, since in QUBO, x squared equals x. The next is the cross terms, those couplers, xi, xj, and you sum. You could start, notice the special counting there, and the 2, you start at 0 on the first sum, and the second sum starts at I, and that way we don't introduce a double count. Then minus 8 times the single sum over those. That comes from the cross term in the multiply, and then a constant of 16. And that constant is going to play a role in this later on, but we can ignore it for right now. So moving on here, starting out as an empty matrix, and the bottom statement there, the default dict that initializes it. In this case, it's just integers, but you could do floats. In this case, it's just int. And what we've got here is I'm going to put in these cross terms first, the term that's in the red box. And you can see there that the 2's on the diagonal are all the same, and they're all there, and they're all 2. All of them are included. Some of you that have formulated other problems know that sometimes you don't get them all when you do the algebra. But in this problem, the couplers are all there. And then we go on. So notice nothing on the diagonal yet, but we're going to add the individual terms. There's going to be a minus 8, 1 minus 8 for each x. And starting at the left, uppermost, that's x0, then x1, then x2. And how does that work? Why is it? It's because x0 is the same as x00, which is the uppermost, leftistmost one, corresponding to the top upper corner, the left top corner. That's minus 8. They're all minus 8. Continuing. This has, as I mentioned, a replacement of the xi squared to just x. And so that adds a 1 for each term on the diagonal. So now they're all minus 7. And I've got only one more thing to add in, which is finally to go back and add in the thing that we wanted to minimize. And by the way, the constant gets ignored for now. There's no way to put it in here, but it will be in, as I mentioned later. So here's some Python to do that. We just set up the Q matrix, put minus 7 on the diagonal there. The I terms and the ij's are all 2. Notice the iterating. Not very complicated Python. Now, to put in the objective, what I've got to do is iterate through my edges, and for each one, I've got to add terms xi and xj and minus 2i at 2 xi xj. And the way that works affects the following terms. In this case, we're just picking the edge from 0 and 4, that one across the diagonal. And you'll notice that what we've done is we added a 1 both to the x0 term, that's the top left, and then the fifth one is the now a -6 there in the middle. That's the number 4 term. If you think about it, the -6 on the top left is 0, then 1, then 2, then 3, then 4. And finally, we also have to add a 2 in, or excuse me, subtract a 2, and that negates the coupler that was there. There was a 2 there, now it's a 0. And if I then continue and do all of them, I can just write that in a loop. And just a brief mention here, this programming is an example of kind of doing hybrid work, even though we're going to use the QPU, Quantum Programming Unit, directly. But in Python, we can do a lot of this stuff that Python is good at, like looping. And we're going to send the actual problem, the hard part, to the quantum computer. Okay, what happens when we run this program? And if you want to see what the program looks like, it's on the right there. I'll just mention a few things about this. This is part of what I'm so proud of with the D-Wave Ocean API, is that there's a lot in this little program. They really sought to make the API something that would not require a lot of code, but would have a lot of power underneath it. And in this program, they're using a open source utility package called NetworkX to make a graph on line 5 and add the edges in. Those are those edges I talked about. Then those pieces of code I talked about before with the queues, setting up the QUBO. Finally, then on line 22, we send it to the quantum computer with 2 steps. The D-Wave sampler is the step that sends it to the quantum processing unit. And then the embedding composite wrapped around it says, hey, quantum computer, embed this problem on your graph. There's a video about embedding if you're interested in that. But it basically says, take this logical problem that I've coded for you here and put it onto physical qubits and give me back a sampler so that then on line 23, I can call that sampler with using what's called the sample QUBO method. And we're doing something here where we're only telling the quantum computer to run it 10 times. Not very exciting. Most of you, if you've done this, have done thousands. But in this case, we're just proving a point of how to do it. And at the bottom on line 25, we're just going to print out the output, the sample set. In other words, what came back. And we do it on the left. And let's say a little bit about this. Notice the row with the 0. The farthest left column starts with a 0, and it's got 1s and 0s across. 1 0 1 0 1 1 0 0. Hey, that's pretty good. That does have 4 zeros and 4 1s. Hopefully you can see that. And the one below it, row 1 there, has the same feature, the same attribute. That's good. But there's an interesting thing that happens here. This is telling me that the minimum energy is -14, and I got 2 solutions. So when I first saw this slide, I wrote my own program and ran it, and the next time I got 4 solutions, and then I got 2, and then I got 4. And what is this telling me? It's probably saying that I might want to think about this a little bit more. How do I know how many there are? I should probably think about this a little further. And let's go on. What we have forgotten, it turns out the first thing is this Lagrange parameter that I talked about before. Remember how in the QUBO there was that funny thing gamma there that I needed to put in to weigh the constraint. And the reason we do that is that if we don't put that in there, or if it's too small, the constraint might get violated, because the quantum computer is going to find solutions that will minimize the other part, but we want that gamma term to weigh more heavily. And so notice what I did on the right. On line 11, I set Lagrange to 4, just guessing. And then I changed the equation so that now it's 7 times Lagrange, and that is minus 7 times Lagrange, and 2 times Lagrange. And notice that on line 17 and forward there, I do not put the Lagrange on that one because those are the objective. It's the constraint that gets multiplied by gamma. And you can see how this is going to work. I've got a number of edges, and Lagrange of 4 is going to do a better job of weighing it versus the other. Now, what happened? I look at the bottom, and I've got a minus 59, and something on the right says chain something is 0.75. What's going on? This is an example of what is called chain break. Okay, what am I talking about? What has happened here? Remember I mentioned the embedding that occurred in that embedding composite on line 23? What has to happen here is that the graph that we put in on line 6 is not naturally found on the D-Wave quantum computer natively because the couplers are not naturally going to connect. For example, 1 and 2 there. If I tried to map each logical variable or logical qubit to a physical qubit, it doesn't have a coupler between 1 and 2. And so what I have to do is do an embedding trick, which is that I make chains. I make, say, the logical variable 1 in that line 6 maybe gets represented by 2 or 3 physical qubits. And what this is telling me is that I didn't really get it quite right because I've got chain breaks. And what happens there is that the solution that comes up, like in other words, if I constrain 2 qubits to have the same value and try to get the computer to do that, it might not be able to because of other numerics in the problem. And here's the deal. What has to happen is I have to add a number called the chain strength when I solve it on line 24. And so take a look at 24 there. Sample set equals sampler dot sample cubo of Q and num reads. You see that? Notice how I put in the chain strength there equals 10. How did I guess 10? I guessed 10 because that's on the same order as the Lagrange parameter of 4. In other words, I'm not guessing 0.1. I'm not guessing 1,000. I'm trying to guess something on the same order to start. And it turns out that solving problems by the D-Wave quantum computer does have these parameters. You have to search around a little bit with these. And we could try it with different values of chain strength and, yes, different values of Lagrange. And I'm going to show you here what happened. I got good results right away. And what happened here is that the energy came out to minus 62. Notice that that first line has 4, like it should, and number of occurrences is 2. And notice that the green lines on the right, those are red and blue. You see that? In other words, red and red across the middle doesn't cause a problem, but red and blue is what I wanted to minimize, and I ended up with 2 of them. And the question is, can I do any better? Should I be able to do any better? Let's talk about that a little. But before I do that, notice that on the right now, on the left side, that chain variable, which stands for chain break fraction, is 0. So the chain strength has done its job. And I'm going to put in a little plug for a recently released piece of software called, by D-Wave, which is a problem inspector. And you can get that you can download and run it yourself as part of the Ocean Toolkit. And it does a great job of showing graphs. We didn't do that in this case. But that's part of February's release of LEAP 2. And I'd encourage you when you sign up for LEAP to make sure you try these things out. Now, the fun part for me is after we get a solution, and thanks to Susan for mentioning I have a physics background, they always taught us, is this a good solution? Is it optimal? How many there are? Should I have more? What is energy minus 62? And this is the point. Remember that constant all the way back a ways ago that I said we're just going to put it aside, and it was 16? It wasn't really 16. If we do the algebra, it was 16 times the Lagrange parameter, but the Lagrange parameter is 4. So if I add a 64 to minus 62, the minimum energy is 2. Does that make sense? Well, yes, because there are 2 red and blue links. See them? And the way I set this problem up all the way back was that any red-blue link is going to get penalized an energy of 1. So therefore, if I run this problem, I should see a certain number of 2s, right? I think that that's the best I can do. And I'm going to leave this to an exercise for those of you out there who are mathematically minded. Can you show that there are no more than that? Now, all of you out there with big problems, you're thinking, how do I know how many there are going to be? And part of that is encouraging you when you first start and run your problem, you are going to have to run it a number of times and look at it. And the good solutions and the clear solutions do start to make themselves known. You start to get intuition. It's like any other technical problem. You first start and you're not sure. But I always tell people to start with a small problem of 2 or 3 satellites instead of 40, or 4 stocks instead of 60. Make sure that you're getting something you understand so that then when you run it on a bigger problem, you can trust what it's doing. Okay, so you've got a little bit of an assignment, and let's wrap up here. I've got a couple more things and then we'll go to questions. Please sign up for LEAP. The link is there in the middle of the slide. And if you haven't, go ahead. You get 1 minute of QPU time per month. If you give us your GitHub ID, that is, you can have it per month indefinitely. Your first month is always a minute, even if you don't give us your GitHub ID. But a minute doesn't sound like a lot, but it is. Each individual trial, each individual run is on the order of microseconds. So you can run 1,000 trials in a milliseconds order. And so you can do a pretty good amount of work with a minute of QPU. So please do that and look for the newly released software, the Problem Inspector, and also the LEAP IDE for those of you that like programming in IDEs. I'm too old, so I tend not to, but for those of you who like to. One more thing is that Victoria, who wrote this deck, also produced a guide to formulating problems, which goes over some of the same terrain that we just did. So please take a photo of this one if you'd like to get this link. It's on the D-Wave documents page also, docs.ocean.dwavesys.com, or possibly I think also docs.dwavesys.com. And I encourage you to play around with these tools and enjoy all of it. You're programming a quantum computer. This is new stuff. In 20 years, it'll look like old stuff, but for right now, it's very new. So to close up, thank you very much for listening. I'm Joel Gottlieb. Please email me if you have any questions for us. And I hope you've kept the panel busy as well.
Hey, thanks, Joel. They certainly have kept the panel busy. Panel is busy. We've answered a lot of questions. We'll ask some more. out loud now. We had a number of questions regarding some of the material and getting started. So once you sign up for an account in Leap, you will see a lot of resources there, a lot of documentation, interactive examples and demos. You'll see how to work with the Ocean tools, the new problem inspector and IDE. So that really is the first place to start. There's also a very vibrant community. So if you have questions while you're going, you can post questions there and there'll be somebody to answer. So a few other things before I start asking the questions. This webinar is being recorded and it will be on YouTube over the next few days. We will also send out an email with a link to the slides so that for those that are looking for the presentation material, you can get that as well. Oh, and thank you to someone who just said this is the best webinar of your series. We appreciate that. So here's some questions for Joel. First question, is it possible to transform all traditional algorithms into quantum algorithms? I have recently read that there are some limitations.
I love these questions. I would say, I don't know is the honest answer. I think right now, so let's answer this first right now. For both D-Wave with the annealing and for gate model, definitely not. There's a lot of stuff out there that just wouldn't really do any better at this point. I think the world is waiting for people like Peter Shor, unexpectedly in 1994, coming up with the Shor algorithm and showing possible quantum improvement, and the Glover algorithm. I think the world is waiting for a lot of that work. Will it eventually happen? I think so, but I think it's going to be a while, partly because where quantum computing so far has shown the best is in optimization problems, but there's a lot of other algorithms out there, and I'm not an algorithm specialist myself, so this is going to go out of my own expertise. But for right now, yes, there are limitations, and I would encourage the person who asked that to try it. If you've got something that you're interested in, try it out, because so far D-Wave has, I think, 250, something like that, papers or presentations that we've seen, and that's what you want. We all want to do this so that we get to everything eventually. That's a great question.
Okay, next question, and we had a few people asking this in terms of really what kind of background or information they need in mathematics or physics to be really good at to work on quantum computation on D-Wave.
Yeah, so first of all, it requires some algebra. We have had some internal discussions about, is this really high school algebra? I think so, but a lot of people don't remember very much from high school, and they take it, as a first course in college. In terms of physics, D-Wave has worked very hard to make this programming interface and this API not heavily physics dependent. So much so that when we train people now, we don't do as much physics, and because we don't need to. The gate model programming, our competitors like IBM or Google, those do require more physics in the programming. I think in both cases, someday the tools will be there, but that's an aside. My main thing is, I don't think any background is honestly required as much as a willingness to consider new information and think in a new way. And the reason I say that is that we've had people come to our training classes from high schools, from completely different backgrounds with no technical background at all. And they just sit there and they just ask us questions, and we answer them. And if something mathematically bothers you, you just ask somebody or look for our message boards and put the question there. Things like that. I guess I see those t-shirts a lot that say no fear. And I kind of think of that all the time. Like, no fear of this sort of thing. Like, whoever's out there, if your background isn't in this, that's okay. because you can pick up the stuff. I think yes, there would be aspects of it that would be harder if you didn't have the background. And yes, there might be physics in it if you wanted to go into really advanced stuff. But to get somewhat involved does not require very much background. And to me, the overall thing is that willingness to engage the new information and figure it out.
Great. Thanks, Joel. There was another question that was actually already answered, but the panelists thought I should ask it out loud. So it said, what difference does it make when using Kubo versus Ising? I'll also just read out the answer, and I will post a link in the chat box. The answer being Ising and Kubo are two equivalent formulations that can be mapped onto each other. The choice depends on the particular problem you're dealing with. And in the chat box to everyone, I'm going to put the link. So if you're interested in Kubo versus Ising, you can take a look there. All right, let's go on to some more of the questions here. Does the size of the multiplier affect the speed of optimization? If so, how do you tune it?
No. In terms of the speed, that is, of the quantum computer itself, no. The hardware runs each cycle on the microsecond order, and no, the size wouldn't matter to it. In terms of the speed of getting to a good answer, if you wanted to look for that, in other words, you start out like in that problem, I did 4 and I did 6 and I did 10, whatever. Yeah, there might be more parameter space to explore depending on what realm you're in, but it tends to be more of an advanced question for people that do this work all the time as to worrying about things like that. So in general, though, no.
Okay, next question, Joel. I'm going to move you along because we have quite a few here.
Sure.
Is there a method of intelligent guessing these variables in question?
What we do first is just on the same order as the other terms in the Kubo. If the Kubo terms are 100, guess 100, that kind of thing. Down the road, it would be great if somebody wrote machine learning software to to find it. That has not happened yet. So I would say no, there is not anything intelligent out there yet.
Okay, next question. Are the Lagrange parameter and chain strength used to tune the final solution? Do you use different combinations to get the optimal solution?
Yes. You can think of it as a grid that you would try combinations in both. You would want to hone in first on a general place, on that big chessboard. And then that's a good analogy. Like it's a chessboard of values. Find the rough chess square that you're on, and then hone in within it to see how close you can get.
Okay. What types of problems can be better solved by a quantum computer?
Yeah, the great question. We believe that at least initially, there are two kinds, I think, that have shown the most potential. One is optimizing problems like stock picking and team selection, like we showed, graph problems like that. Another is material science, which our colleagues Andrew King and Richard Harris have been researching. That work is slow because that's very physics intensive. There's a lot of people that talk about machine learning, but that's an early phase for that one. So I think the first two are the material science and the optimization, really.
Okay, well, we have a lot of other questions, but we are rapidly running out of time. We will be able to download the questions that haven't been answered yet, and we'll make sure that we send answers back. We can also post, if you haven't seen the questions, we can post the questions as well. So when we send out information about the slides, we'll make sure those are available as well. Just quickly see if there's...
Yeah, can I make one comment on the Ising versus Kubo statement?
Sure.
Whoever asked that, that's marvelous. That's a good question. And everybody wants to know this. So it has been stated that problems, if you really dig into it, Ising should perform better on the QPU because it's its native architecture. In other words, Cubo problems have to be transformed mathematically into Ising in order to run. However, you got to know your details and how to gauge what does it mean to perform better to do that kind of work. So at the level of this talk, either works. I think the jury's still out. Can we show advantage one or the other? It would be a hard thing to do.
Okay, well, with that, we're going to wrap up. We thank you all so very much. Again, we would be very interested in what you think would be most useful for you in future webinars. We do these monthly. If you look at the YouTube channel for D-Wave, you'll see lots and lots of topics, some designed for people that are new to it and some designed for people that have been working with quantum computers or D-Wave systems for a while. And again, we encourage you to go sign up for LEAP if you don't already have an account, because there's just a ton of information and great education and learning through what's available there. So thank you so much, and we look forward to having you attend a future webinar. Bye-bye. Stay well, everyone.
Bye-bye.